And now let's make a quick exercise. Okay, we will just figure out that we have a working environment for a robot where there are a set of coordinate frames associated to one element of the operating system. The first coordinate frame is the world coordinate frame. Outside the robot is a fixed coordinate frame to which finally we will end up referring all coordinates. In the robot space, there's also a coordinate frame associated to the robot. Okay, that's logical. In general, we are talking about the base of the robot, the non-mobile part of the robot. Okay, this coordinate frame is represented by R. Then there's a camera at the end of the robot which will move as the robot moves. Okay, the values of the joints will determine the position of the camera. The coordinate frame represented the camera of the robot is C. Then we will suppose that the robot is interacting in some way with a physical object. Okay, the material with which we are doing operations. This object is attached to a reference frame B. And let us also assume that there is a fixed camera outside the robot. Okay, this will complement the information given by the moving camera attached to the robot. Okay, this is the fixed one and it is attached to coordinate frame F. So we have 5 coordinate frames and we will see that there are some transformations between all those coordinate frames. In this exercise, we will see how we compound transformations. Okay, so we will relate each coordinate frame to the origin by doing the following. Well, first of all, assume that we have the homogeneous transform matrices of that appear in this drawing. Okay, so we have this. I will slightly amend this drawing by substituting this chi symbol by T. Okay, because in the following we will use T. Sorry about that, but this is a drawing coming from the book. The book uses an intermediate, more abstract object that is called chi, but we will not use it. We will call this T. Later, you will understand why it is easy to call everything T. It's simpler, okay? Now, observe that there are a set of matrices. We have this 0TF matrix that has the same meaning as the homogeneous transform matrix that we have just defined. Okay, this 0TF matrix is the one that we would use to transform coordinates from reference frame F to reference frame 0. Okay, so whenever we have a point in this space, right, in F, if we have the coordinates expressed with respect to F, then we will have PF. If we want to change the coordinates of that point to frame 0, we will multiply it by the homogeneous transform matrix T0F, and this will give us the coordinates of that point in the 0 frame. Okay, this is what we have just explained. I will not go into the detail on how to compute TF, but this is exactly what we have said before. In order to compute TF, we will need to know what are first the translations that have to be done on the O frame to reach the origin of the F frame, and then we should write down the rotations to reach the final orientation of the F frame. Okay, So if we have that information, we already know how to compute the matrix 0TF. But this exercise is not about that, okay? Just another reminder, this row is important. This row should be understood that in some way f is reference with respect to O or with respect to 0, okay? It does not mean that the coordinate change is from 0 to f. All the way around. This arrow means that 0 TF will change coordinates from f to 0. This, if you have properly understood the previous discussion, then this should be clear to you. Okay, so let us erase extra information that we don't need now. Okay, this is the setup that we have. So, assuming that we have all these matrices, that's all these matrices, assuming that they are given to us, how could we compute the transformation matrices that transform any coordinates from any of those reference frames to the origin? That is, we are being asked how to compute not with respect to the origin, sorry. We are requested to transform all coordinates to the robot coordinate frame. And how do we do that? So we have to compute all homogeneous transform matrix with respect to the R frame. Okay, so we are being requested to compute the transformation from C to R. Then we are requested to compute the transformation from B to R. Then the transformation from F to R. Okay, so that's how we would express the coordinates. That's how we would change any coordinate expressed, for example, in the C frame. This will give us how to change those coordinates into the R frame. So in order to do that, we have a white page next, and let us just analyze what is. Let us just start by C. TCR is the matrix that will transform from PC to PR. And we actually have this matrix. So as this is a given data, TCR is does not need any computation. Let's go to the following. How do we obtain TBR? Well, TBR, that is the matrix that we transform from B to R, is a matrix that is not given here. But just observe something, okay? Imagine that we transform from B to 0, okay? So transforming from B to 0, let's write here from B to 0, we would have P0 equals T0 B P B. And this matrix is given. Now, this is first step. Second step, how do we transform from 0 to R? From 0 to R, we would have this PR equals some transformation matrix R0 P0. Okay. So now just join these two expressions together, and if you write the first one, P0 equals, I will just erase this. I will use the second expression, PR equals RT0. And then instead of P0 from the last equations, we will go to this one, and we will substitute the right-hand side, so we have T0 B P B. Okay, so the multiplication of these two matrices, undoubtedly it will result in T0 B. Okay, so and this is one of the metrics that we have been asked for. So if we write this relation in just one formula, we will write RTB equals RT0 TB. Did we solve the problem? Not yet. Not yet, because this is given, but this is unknown. So we will further develop this element in terms of elements that are given. Now, if we go to the drawing, the matrix that we are given is 0TR and not RT0. So in order to have RT0, it is clear that we have seen also in the previous explanation, RT0 is equal to 0TR to the -1. It's the inverse. Okay, just invert any changing coordinates relation, and you will have the opposite change, right? So now we substitute this in here, and we end up having RTB equals 0TR to the -1 and 0TB. And this is the solution to the first, let's say, the first question about computing RTB. Summarizing, we are looking for a matrix that transforms from B to R, okay? Because the question is, what are the homogeneous transforms that change from all those coordinate frames to R, okay? So we are looking for this change, so we are looking for this matrix. But in order to find out this matrix, we observe that we don't have a direct change from B to R, but we have an indirect change from B to 0, and then a change from 0 to R, okay? So we make this path. Let's take a look at it in the drawing. I'm going to highlight that in green. From B to R, first we go from B to 0, and then we go from 0 to R. Okay, and we observe that in that path we have these two matrices. Okay, so that's why first we write the equation for changing from B to 0, and then in that expression 0TB appears, and then we apply the second step from 0 to R, okay, from 0 to R, and in that expression RT0 appears. So joining these two steps, that is writing the second equation but substituting for P0, we would have that from B to R, we would have these two matrices, okay? From B to R, we will have these two matrices, which means that if this matrix product changes from B to R, then this matrix product is necessarily RTB. Okay, so RTB is equal to RT0 0TB. So it might seem that we have already computed RTB, but it is not the case, because 0TB is given, but RT0 is not given in the initial drawing. Okay, in the initial drawing we have 0TR. So how do we obtain RT0? RT0, which is the missing matrix. But this is trivial. Whenever we have a matrix that transforms from 0 to R, the inverse RT0 is 0 tr to the minus 1, or the inverse of 0 tr. I have to make a small comment. The inverse matrix of 0 tr is not the same as the transpose, okay? It only happens for rotation matrices, but the homogeneous transform matrix has more than a rotation matrix. It also has the translations. And if it has a translation, then it breaks the orthonormality of the matrix. So we have RT0 equals 0 tr to the minus 1. And then this matrix is given. So now I can rewrite this formula using this expression, and then we have RTB equals 0 tr to the minus 1, 0 tb. Okay, so at first sight it might look complicated, but it's very simple. And you will become accustomed if we solve the second example. So we had RTC was given. This has just been computed. Now let's move to FTR, right? So how do we transform from F to R? Well, from F to R, we will follow exactly the same steps. We are transforming from F to R. So in coordinate equations, we are looking for a matrix that transforms coordinates from F to R. How do we deal with that? Again, we will find an indirect path for getting from F to R. And this indirect path is actually obtained by following steps that are known. And this is, I'm going to use the green one. I'm going to delete everything in here because otherwise we will go somewhat crazy. Yes, okay. So, removing informations. Now, let's use the green highlight. And then for getting from F to R, first we have to follow this path. There could be other options, but this is the one that we are choosing now. First F to 0 and then F to, okay, sorry, I lost it, right? So F to 0 and then F to R, right? That's the way we are going to change from F to R. So let's, okay, let's first compute the change from F to 0. And this would mean P0 equals TF0 PF, right? And then second step from 0 to R, which would mean PR equals RT0 P0, right? So now we have the following. Okay, well, I need an extra page. This will make me yes, okay. So the first step is based on which transforms from P to 0 is based on the matrix TF0, which is given. Okay, remember that in the drawing we are given this matrix, which is T0F. Right, so second step is from 0 to R, which is done with this matrix. And this is the same case as before. We have to rewrite the second equation as PR equals RT0, and then substitute P0 from its expression in the first equation. So we will substitute for the right hand side, and then 0 TF PF appears. Okay, and then by using the definition of the transformation between F and R, then this is the definition, okay, R, then we will equate these two matrices. So the matrices RRF, the matrix RRF is equal to the matrix RT0 multiplied by the matrix 0TF. So let's just write this equation. RT F equals RT0 0TF. Okay, and RTF is the expression that we are searching for, and 0TF is given, but RT0, as before, is not given. But we know that by definition RT0 needs to be the inverse of 0TR. Okay, in order to check that, you would just need to invert the relation between invert the matrix relation between coordinates and coordinates in 0 and coordinates in R. So this is just the inverse. So we can substitute, we can substitute this inverse right in here, and now we have the right hand side in terms of matrices that we already know. So just to write it in a single line, RTF equals 0TR to the minus 1 multiplied by 0TF. Okay. Well, the third case is computing okay, we have the RTF, and RTF and RTC, which is we had already done. So we have done all of them. Some comments. When we have decomposed a coordinate change in a series of steps, we observe that there can be, for example, if we want to go from some coordinate frame AB, then we will always have T AB, that is from B to A, will always be equal to the transform from some coordinate system X to A multiplied by the transform of B to that intermediate coordinate system. And this is actually the thing that we must remember. Okay, so let's think about matrices as things that transform from the coordinate frame that appears in the lower right subindex to the coordinate frame that appears in the upper left superindex. Okay, so from B to X. And now what happens is that after multiplication from the right of this matrix, we will have here, of course, coordinates in X system. So the matrix that multiplies on the right shouldn't necessarily have coordinates in X frame as an input. Okay, so this superindex should be the same as this lower right subindex. Okay, and this is the general rule. Let us simplify and remember, whenever we have a transformation from B to A, this should be decomposed from the right to the left, from B to some intermediate coordinate frame X, and then from X to A. Okay, remember, these always should be together, right? And the second thing is inversion. We have used inversion. That is, if we have a couple of coordinate frames, the transformation from B to A is always the inverse transformation from the inverse on the transformations from A to B. So that's the end of the exercise, and this is the final discussion. And remember that we can introduce an intermediate coordinate frame in any coordinate change, but this intermediate need not be only one step. There could be more coordinate frames in the middle. So if I think that from getting from B to A, we have imagine that we have more steps, like, so if from B to A we have more steps, like first we should go from B to X, then we should go from X to Y, then we should go to A, then the composition would be, and I think that there will be no trouble with you if I write the whole thing in a row. Then I will have TBX, then I will have TXY, then I will have TYA. And in all steps, I will respect the rule that the two frame from the right matrix should be the from frame of the in matrix. Same happens as here. The two frame of the right matrix in this multiplication should be the from frame in the left matrix. Okay, I think that that's all for now.